Hello all, welcome to the next session on electronic devices. In today's session, we'll be starting off with 6th topic of module 4. We are done with the fabrication process of MOSFETs. We had understood how to create an N-channel enhancement type MOSFET in the previous class, and we had also gone through various steps that is involved in order to fabricate an N-channel MOSFET, right? In today's class, first we shall understand what is the different configurations that we have, what are all the different Mosfet structures that we have. As we have already looked into, there are two basic classifications. One is enhancement type MOSFET and other is depletion type MOSFET. Again, in enhancement type MOSFET, we have two classifications, which is N type and P type. And again, in depletion, the same N and P types comes into picture. Therefore, so it is very much important for you to understand what are all the basic MOSFET structures that we can come across for all these 4 different configurations. And once we are done with that, then we'll take up an N-channel enhancement mode device and try to understand its operating principles, and then we'll consider the depletion mode N-channel MOSFET and then try to understand its working principle and the characteristics. So once you are done with the N channel, then you can relate that with the P channel very easily. Yeah. So we'll start off with the MOSFET structures. See, in between there are 2 topics which is related to energy band diagrams, that is 4.4 and 4.5, which is about the capacitor voltage characteristics, that we shall take up later once we are done with the explanation about the operating principles of the MOSFET. So until and unless you understand this, it is very difficult to understand the next 2 topics. Therefore, first let me cover this and then we'll go for the energy band diagrams. Done. Now, what is that we are trying to discuss here? It is the MOSFET structures that we are trying to understand. Now, what are the 4 different configurations I told? Whenever I consider a MOSFET, what are the 2 different classifications of the MOSFETs that we have? One is called as enhancement mode MOSFETs and the other is referred as depletion type MOSFETs. Again, when I consider the enhancement, there are 2 different classifications. One is called as N channel and other is called as P channel. And then here again in the depletion mode, we have N channel and P channel. Done. Now, we will try to understand how to represent an N-channel enhancement mode MOSFET, a P-channel enhancement mode MOSFET. Similarly, for the N-channel depletion as well as P-channel depletion. Yeah, all those 4 you have to understand. Along with that, you should be able to represent the symbols for the same as well. So, very first, let me try to consider the N-channel enhancement mode MOSFET. What is the very basic first structure that I am considering? It is N-channel enhancement mode MOSFET. Done. Now, as I told, what kind of channel is getting created? It is the N channel that I should have. See, always remember, whenever you have to have an N channel, the underlying substrate that you should have should be of opposite type. Therefore, the kind of substrate that I should have is a P type substrate. Done. After that, within the P substrate, I will be having 2 wells and both of these wells are made up of N plus materials. Which kind of channel is this? N channel. Therefore, the wells should be of same material. Underlying substrate should be of the opposite type. Remember this. That's the key point that you have to understand. Now, this N plus, let me consider the ohmic contact or the metal contact that I have, and then the source terminal, and then here this forms the drain terminal, and then in between these 2, what we have? We have another terminal wherein we have an oxide layer followed by a metal layer, and then that forms what is called as the gate terminal of the MOSFET. What are the two layers here? We have, it is the silicon dioxide, or it is called as gate oxide. What is this? This is an insulating layer that we have, and the thickness of this insulating layer is very thin. It will be in terms of angstroms, which is in and around 1000 angstroms. Done. And then above that we have a metal layer, and from there we are trying to get the contact for the gate. And then one more thing that we have, one more terminal that we have is what we refer as body, or which is also referred as substrate. Done. Usually we say the MOSFET is of 3-terminal device which contains the source, gate and drain. But along with that, there is actually one more terminal that we have, which is called as body or the substrate. But what we usually do is we always ensure the body and the source, both of these are shorted together and they both are at the same potential. Henceforth, they will not mention this explicitly. Instead, they will consider only these three, because we know the source is always at the same potential as that of the body or the substrate. Done? Clear till here? So this is how I will be representing for which kind. It is for the N-channel enhancement mode MOSFET. Now let me try to represent the symbol for the same. Yeah, before going into that, let me try to represent the cross section. What is this called as? This is the cross sectional view of the N-channel enhancement mode MOSFET. Now let me try to represent the cross sectional view of N-channel depletion mode MOSFET. So once we are done with these two, then we'll go for the P channel. Done. So what is that I am considering? It is N-channel depletion mode MOSFET. Now, the enhancement and the depletion mode is almost the same, except there is a single difference between these two. What makes the difference is, I already mentioned, when I consider an enhancement type, there is no channel that is present between these two, whereas when I consider the depletion mode, there exists a channel between the source and the drain. Yeah. Now, one more thing I forgot to mention here is the depletion regions. How will I mention those depletion regions? Let me just shade it across. Now, we know what are these. This is an N plus layer and this is the P type material. This is an N plus material and here we have as a P type material. So, whenever two different kinds of semiconductors comes in contact with, what is that we have? There exists a depletion region, and that depletion region is what I am trying to represent now. Done? Don't forget to represent the depletion regions. Now let me continue with the depletion mode MOSFET. Now what all we have in the depletion mode MOSFET? We have a substrate. What kind of substrate have to consider? Since it is an N channel, the opposite type of the substrate I have to consider, which is that it is a P type substrate. Done? Now once I am done with the P type substrate, then what I have to consider? It is the two wells that I have to form. What are these two wells? It is made up of N plus regions. After this, what is the next thing that we have? Here it's an oxide layer followed by a metal layer. Here we have an ohmic contact, again here we have an ohmic contact, here also we have an ohmic contact. What is this? Body, or in the short form we can represent it as B or substrate, and this is the source terminal, this is the drain terminal, and this is where the gate terminal comes into picture. Done? Now, what makes this different from that of the enhancement type? There already exists a channel. Therefore, I need to represent a channel which exists between the source and the drain, and that is how I am representing. Now, you might question me, how this can be formed is by intentionally doping a layer of N region between the source and the drain. So, when we have that doping, then automatically a channel is being formed, and which is done during the fabrication process itself. And whenever we come across N plus and P, what do we have? We have a depletion layer or a space charge region. Depletion region, so let me just represent that. Depletion region. Done. And this is the difference that you can find between an enhancement mode N-channel MOSFET and an N-channel depletion mode MOSFET. Done. Now let me tell you how to represent the symbol. These are the cross-sectional views. Now let me tell you how to represent the symbol for the same. So if I want to represent the symbol for the N-channel enhancement mode, then we know what are all terminals we have. Like this you write down a structure, and then since it is an enhancement, there is no channel that is being formed. You have to create the channel. See, this is the drain terminal, this is the source terminal, this is the gate, and this is the body. Done. Now, do we have connection between drain and source when I consider enhancement? When my gate voltage is 0. Please remember, when there is no potential across the gate, there will not be any channel, and that kind of device is called as enhancement mode. Even though when my gate voltage is 0, there is already a channel that exists between the source and the drain, and that kind is called as depletion mode MOSFET. Therefore, since there is no path between the drain and the source at 0 potential of the gate, I need to write down discrete lines, that is separate lines for the source, body and the drain, which indicates the gap here indicates there is no channel which is present, and that is how you can differentiate, or you can make out this is an enhancement mode symbol. Now, how can you identify it as an N channel? See, the body is made up of what? P-type. You remember the diode, how does the current direction is always from P to N. You remember that. Therefore, it is leaving P, right? P-type, it is leaving P-type material. That is how the direction have to be. Since the body is made up of P-type, it has to leave. Therefore, I will be writing the arrowhead in the outward direction. So, this is the symbol for the N-channel enhancement mode MOSFET. Or if I want to write it in the other way around, there is also another way through which I can write it. See, all I do is the same. This is the gate, this is the drain, and this is the source terminal. The only difference I do here is I mentioned the source and the body are always at the same potential. Therefore, what we can do is we can chart both of these together, represent the arrow without fail across the body, and this is also another way of writing the symbol for the N-channel enhancement mode MOSFET. Done. So, I hope all of you understood the cross-sectional view as well as the symbols through which you can identify it as an N-channel enhancement mode. Now, let us try to see how to represent for a depletion mode MOSFET. What is that we have? We have a gate terminal. Let me just, this is the drain, source and the body. Or I told you another way of writing it. I will short both the body and the source to be of the same potential. Done. Now, what is depletion? There exists already a channel, right? How will I indicate that? Instead of writing separate lines, join them together, which will indicate clearly that this is a depletion type MOSFET. And then one more thing, here it is of N channel, therefore the direction have to be outwards. Clear? And this is the way in which you will be writing down the structures, Mosfet structures for N channel enhancement type. This is the cross sectional view and the symbols, and this is the cross sectional view of the N channel depletion with the what is called as the symbols of the N channel depletion mode MOSFET. Done. Now, if in case I want to represent for the P channel, then what does that have to do here? So, I will just consider P channel now. Done. Now, what does that have to do? If in case I am considering a P channel, then what should be my substrate? It should be of N type. What should be my source and drain wells made up of? P plus regions. Done. And then here what should be the arrow direction that I have to consider? It should be inwards, because it is N-type. So P to N, you remember the diode? This is P to N, direction like this. So it is leaving P, entering N, therefore it should be inwards. Done? Here also what should be the arrow direction? It should be inwards. And this is the symbol and the cross-sectional view of an P-channel enhancement mode MOSFET. Now if in case I want to do it for the depletion mode, then what does that have to do here? I have to consider these to be as P plus regions, this to be as N-type substrate, and what happens to the body direction of the arrow that I have to put up? It should be in the inward direction. And this completes the 4 different structures that we have to consider under MOSFET. I hope all of you are clear with these structures, how to write the cross-sectional structure and how to represent the symbol of the MOSFETs for all different 4 cases. Done? Now what we will try to do is, under the same topic, now we will try to understand what is the working principle of N-channel enhancement mode, and we will try to understand what is the working principle of N-channel depletion mode. So if you are aware of these concepts, then it is very easy for you to decode the working principle of P-channel enhancement and the depletion mode. Yeah. So the second topic is current voltage relationship, and here we are looking just into the concepts of how these currents and voltages are related, and for which 2 kinds we are considering. It is the enhancement type of N channel and the depletion type. Done? Yeah. So in order to understand this, first and foremost, let me consider the structure of the N-channel enhancement type. So first and foremost, we shall go through N-channel enhancement type MOSFET. Let's try to understand the working principle of this, and then we shall proceed further. I have to consider N plus wells. Done. And then P-type substrate. We have a body, we have a source, and these 2 are shorted together. Then comes the drain terminal, and then we have an oxide layer followed by a metal layer which forms the gate. Done? After this, and this is how I will be representing the depletion region which exists between this N plus P and this N plus P. Done? And this is the body. Now, what I will try to do to this structure that I have considered, what we have to do is, we need to understand what are the different kinds of biasings that it is involved with. So, when I consider the source and the body, I already mentioned they both are at the same potential. Done? Then, there exists a biasing between the source and the gate, and another biasing between the source and the drain. So, what are the 2 different biasings that we have? So, the first biasing is between which 2? The source and the gate, and the other biasing is between the source and the drain. That means I have to connect a power supply between the source and the gate and a supply between the source and the drain. That is the 2 biasings that we are interested in. And the kind of current that is flowing in the device is referred as ID. What does ID stands for? It is the drain current. Done. Now let me explain you how basically things happen in this kind of enhancement type and what is the working principle of that under different conditions of biasings that we have. Yeah. Now whatever the potential, so what I will do first is let me try to ground the body, which indicates that the source is also grounded. After that what I will try to do is, I will try to consider a condition where my VGS, what is the condition I am considering? Case 1. Whatever the drain potential that I am connecting, see I told you what is the potential biasing is between the drain and the source. Here the source is grounded and the drain have to be connected to the positive terminal of the battery. So if I want to provide the biasing, this is the negative terminal and this is the positive terminal. This is how I will be providing the biasing. And which is the other biasing that I have to do? It is between the source and the gate. How will I do that? The source is at the lower potential and the gate is at the higher potential. And this is how I will be providing the biasing. Understood with this? This is for the N-channel enhancement type. Done. And what is this potential named as? VGS, because gate is at the higher end when compared to that of source. So first let me represent G, then followed by S. It is easy way for you to understand. And then comes another potential which is between the drain and the source. Therefore how will I represent that potential as? VDS, because drain is at higher end when compared to that of source. Let me consider it to be as VDS. Done. Now what is the case number 1 that I have considered? Let my VDS that I have considered, let it be a positive voltage which is very small. So what is that I am doing with VDS and VGS, both of them I will consider it to be as a positive voltage. Done. Now think of that, I am providing a positive potential at the gate terminal. That means this particular terminal is having a positive value. Right? What about the P substrate? It is grounded. Now what I will try to do is, whatever this region I have, let me try to magnify and write it here so that you will clearly understand. So what all we have, this is the gate terminal we have, and this layer whatever I writing is the metal layer that I have considered, and below which what is that we have? It's the silicon dioxide or the gate oxide that we have, and let me consider this, that is the body or the substrate. Done. Now what is that I am doing to the gate? I am connecting it to which terminal? Okay. Now I am connecting the gate to which terminal of the battery? Positive terminal of the battery. What about the body or the substrate, which is same as that of the source? So this is basically connected to the negative terminal of the battery. Done. Now when this happens, I am trying to provide VGS here. Now when this happens, what happens to this particular side of the gate? It is having the positive potential. That means the positive charges tends to accumulate at this particular region. What happens to this side? Here it is connected to the negative terminal. Therefore what happens to the charges? It is the negative charges that gets accumulated. Now in between what do we have? It is the silicon dioxide, which is a gate oxide, which is nothing but an insulating material. So does this look like a passive device that we have known? What is that? We have two plates, and upon these two plates we have different polarities of the charges, and in between we have an insulating layer. Done. Or a dielectric medium, which indicates what? A capacitor. So how does this region behaves like? It is a capacitor. Now it is my duty to understand how can this region accumulate the negative charges in case of the N-channel enhancement type. That means whatever the region that we have here, it is the P-type substrate. No? Now here we need to accumulate the negative charges. How does this basically happen? Done. Here it was easy for you to understand because we had connected this to negative terminal of the battery, and that's how it happened. But here in this case, how does it basically happen? And that is what clearly explains the operating principle of the N-channel enhancement type. Now, when I provide the positive voltage to the gate terminal, what is happening? See, when I consider the p-type material, what does this p-type made up of? The p-type has two charge carriers. One is the majority carriers. What are the majority carriers? It is the holes that we have, and the other is the minority carriers. And what are the minority carriers? It is the electrons. Now, when I provide certain positive voltage at the gate, then what happens to the electrons, that is the minority carriers which is present in the p-type? It is of negative carrier, therefore will it tend to get attracted towards the positive terminal, that is the positive potential. As a result, what is happening? Whatever the electrons, that is the minority carriers that we have, they tend to get drifted towards the positive terminal of the gate. Done. As a result, what is happening? There is an accumulation of the negative charges that is present. Along with that, there is another two factors that you have to look into. One thing is, whatever the space charge region that I have, in this space charge region, whatever the mobile charge carriers that we have, that is made equal to the immobile ions present within the region. We know what is immobile ions, which we found in the depletion region. Remember, what about the mobile charge carriers that we have? It is the free electrons and the holes that we have. Done. Now, what happens to the, because of the positive potential, whatever the immobile ions that we have, they tend to uncover themselves. As a result, the holes that we get tend to get drifted towards the downward direction because we have a positive potential and the holes is of positive charge. As a result, what is happening to the holes? They tend to get drifted towards the downward direction. As a result, the number of electrons that tends to move up and then occupy this region increases. And that totally depends on what is the intensity of the positive voltage that I am providing across the gate terminal. That's the first thing. What is that? Let me repeat. When I try to provide certain positive potential, what is happening to the minority carriers, that is electrons present in the p-type, they tend to get attracted towards the positive terminal of the battery. As a result, all of them get drifted towards the gate terminal. See the keyword that I am using, it is drifting towards the gate terminal. And then what happens to the immobile ions that we have? These immobile ions uncover themselves and the holes will tend to move in the downward direction. Done. And then there will be accumulation of the electrons. That's the first thing that you have to understand. And the next thing that I have wanted to tell you is, what is this terminal? This is the gate oxide, which is an insulating material, right? Now, can these electrons cross over this insulating material and get absorbed by the gate terminal? No, it's not possible. We have made the silicon dioxide because we want the accumulation of the electrons here. We don't want the electrons to cross over and get absorbed to the gate terminal of the battery. We want the accumulation of the electrons, and this process of electrons getting accumulated here, that region of operation is called as accumulation region of operation. Done. Accumulation mode of operation. Done. After that, one more thing that you have to understand here is, it is totally dependent on how much of positive voltage that I am providing at the gate, so that it is sufficient enough to get these electrons to drift it towards and get settled below or beneath that of the oxide layer that we have. So therefore, always whenever I consider the gate voltage, I will be defining it with respect to what is called as threshold voltage. Now what does this threshold voltage indicates is, it is the minimum gate to source voltage. What is that? It is the minimum gate to source voltage that I have to provide in order to ensure that the electrons are drifted and are settled beneath that of the oxide layer that I have. So if in case, now let me change this, if in case my VGS is less than that of the threshold, what will happen? Will there be enough voltage to attract these electrons? No. Therefore, there will not be accumulation of the electrons beneath the oxide layer. Done? That's the first thing that you have to understand. So I'll just write it here in the simpler terms. This is the gate terminal I have. What will I do with the gate to source? I have considered it to be less than the threshold voltage. Done. After that, what is the next thing that I have? A drain. What is that I am providing? Some small VDS value. Therefore, I'll write it as plus VDS. Now, when this happens, please note this point. See, if the VGS is less than VT, therefore, it cannot accumulate the electrons here. And then one more thing that you have is, here the drain is becoming more positive, which means to say my N plus is becoming more positive. So when my N plus is becoming more positive, then what happens to this depletion region that I have? Will it expand or will it compress? It will expand, right? And therefore, whenever I write the diagram for this condition, you have to be very, very careful. See here, the source and the body is, both of them are at ground. So there is not much difference that you can find in the depletion region which is related to the source terminal. But when I consider the drain terminal, the drain is made more positive and P-type is grounded, which is the reverse bias condition. As a result, what happens to the depletion region that is being absorbed in this case? It has to widen. Yeah, can you make out the difference between these two? And that is what you have to clearly understand. And this is for case 1. I am not done with the operation yet. I am not completely done with the operation yet. I have just told you the glimpse. So, we will completely understand for the second case. What was the first case? When my VDS is small positive voltage and my VGS is less than VT, there is no enough gate voltage which can attract the electrons and accumulate them beneath this. And then one more thing is, since the drain is becoming more positive, that is N plus is becoming positive, small positive voltage, and then P-type is grounded, what happens to this depletion region? It widens compared to that of this, because the source here is at the same potential of body which is grounded. Therefore, there is no difference that can you observe, that you can observe in the depletion region. This is regarding case number 1. Done. Now, let us try to move in and understand about case number 2. So, what I will do under case 2 is, I will consider the VDS still to be as small positive voltage, but one difference that I will do here is, whatever the gate to source voltage that I have, that I will make it greater than that of the threshold voltage that I am providing. Done. Now, when I make this happen, let me just write the structure. The source, what am I doing with the source? Let me just ground it. And then what do we have here? Oxide layer and a metal layer which forms the gate, and then we have a drain. Now, what is the condition I am giving here? I am making my VGS greater than VT and still I am providing the VDS. Done. Now, see, when I am providing VGS greater than VT, what is happening? Uncovering of immobile ions takes place, and also the electrons which is present in the P-type, which is the minority carriers, tend to get drifted towards the upward direction. As a result, there is accumulation of the electrons in this particular region. Done. Now, when there is accumulation of the electrons, see, one key point that you have to understand here is, when there is an accumulation of the electrons, see, the kind of substrate that I have is a P-type material, but here the kind of region that is created beneath the silicon dioxide is of electrons. Therefore, within the p-type, what am I trying to do? I am creating an n-type layer. Therefore, this kind of mode of operation wherein you have created a different layer which is totally different when compared to that of p-type material, that kind of operation or the mode of operation is called as inversion mode. And the layer that we have formed, the channel layer that we have formed is called as inversion layer. Why we are calling it as inversion layer? Because within p-type I am trying to create the layer of electrons. So the p-type is totally inverted compared to that of electrons, right? That is the n-type. Therefore, an inversion layer is formed within the p-type, and that's what we refer. Understood with this? Done? Clear till here? Yeah, so that is what you are supposed to understand. And then one more thing that you have to understand is, as we have a layer of electrons, this is also made up of n plus which has majority of electrons. This is also is made up of n plus which has majority of electrons. Now if in case I provide certain positive potential between the source and the drain, that is the positive VDS, when I provide, what is happening to these electrons? These electrons tends to get attracted towards the positive terminal of the battery and thereby starts the current flow. So how is the electrons getting moved from? They tend to move from the source to that of drain, like this the electrons is moving. Therefore, what happens to the conventional current that is flowing in the device? It has to be from the drain to source. How is the electron flowing? From source towards drain and then to the positive terminal of the battery. That means how is the conventional current? It has to be from drain to source. Therefore, let me just erase this. Plus VDS is sufficient to indicate that I am providing certain positive potential between the drain and the source. Therefore, how will I indicate ID? This is how I will indicate. And here also it is very much important for you to write down ID. Done. Here the depletion region width still remains the same because you are trying to provide more amount of drain voltage positive, right? Therefore, it has to be widened when compared to that of this case. Yeah, and then there is a formation of the channel that is taking place between the source and the drain. That's why I have wiped off. Now what is there here? What all we have? We have electrons here. How is these electron moving? It is getting attracted towards the positive terminal of the drain. Hence the conventional current is in this direction. Done. Now one thing you have to understand here is, there was a channel before? No. Now when I increase the voltage greater than threshold, we created a channel between the source and the drain. We try to create, that means we try to enhance a channel between the source and the drain. Thereby we got the name enhancement type MOSFET. There was no channel before. Because of the application of the gate voltage greater than the threshold, we created a channel between the source and the drain. We enhanced a channel, and that's why it is called as N-channel enhancement type. Which kind of channel we created? It's a channel of electrons which is nothing but N-type. Therefore, the name N-channel enhancement type MOSFET. Done? Clear? And this is an introduction with respect to the operation. We still have a long way to go. We have to understand how it varies when the VDS is varied. So that we'll take up in the next class. Thank you one and all. Have a good day.